Hello everyone. Today we are going to set up our Cadence for 45 nanometer technology design kit, and we are going to implement one simple CMOS inverter and its power and delay calculation. So in order to do that, you need to start your Xming first. So double click on Xming and you can see the minimized Xming window over here at the right bottom corner. After that you need to start putty and select the default server which we have previously saved for our CAD server. There will be one pop-up window and you need to log in into this particular server using your e-reader ID and password, so go for it. And note that whatever you type in the password, it is not visible in this particular window, so make sure you write it correctly. So after the login, you are supposed to create one directory in order to copy all those files or do all your projects in the particular folder. So we will make one directory by the name Cadence and we'll use this command, that is mkdir. So type this command, and I'm not going to try this command here because I have already created this directory before. So if you want to check whether your directory is created or not, you just type ls, and this command will show all the folders and files which are there in your directory. So you can see this directory over here, that is Cadence. Now once you created this directory, you need to go into that particular directory. So type cd followed by the name of that directory, which will take you into that particular directory, that is Cadence. You can see that in the path as well. So after that, type the following command which will copy the data from the server to the directory. So type cp and followed by the path which is mentioned in the PDF file. Make sure you give one dot at the end as it is a part of that command and press enter. So all of the files are successfully copied over here. So now in order to access that particular set of file, type the following commands: csh and followed by the command virtuoso, which will ultimately open the Cadence for you. Now you can minimize the windows, you can minimize the putty. There will be 3 windows. One will be just information about the Cadence, you can close that. One is the library window and the other is the log window. Log window is the most important window in Cadence as you need to keep it active while you are using Cadence, so we'll just minimize it for now. This window will give you information about all the activities that you are performing in the Cadence, so we'll minimize it. On the left side of this library window, you can see all the existing libraries in the Cadence 45 nano. These particular 2 libraries are especially for Cadence 45. Now in order to create your own schematic, you are supposed to create your own library. So go to file, new, and library. Type the name of your library, let's say it's demo. Click OK, and there will be one pop-up and it will ask you whether you want to compile that file as an ASCII file or to refer it with the existing technology library, or to attach to an existing technology library, or do not do anything. So among these four options, you are supposed to select the third option and then click OK. Then it will give you one list of libraries. So select the first library from that is FreePDK, which is associated with the Cadence 45 Nano. Click OK. Now you can see your library over here, that is demo. And in order to draw the schematic, select that particular library, go to File, New, and Cell View. As we are going to demonstrate an inverter, type name of that particular schematic. You can give any name. Type will be the schematic only, and click OK. It will ask you for the license for the first time, then click yes, and it will open one schematic window for you. Now we will be using some shortcut keys which I have already mentioned in the PDF file. Here are some shortcut keys like I for inserting component, C for copying, Q for editing properties, M for moving, and so on. So we'll be using some commands, that is shortcut keys over here. So go to your schematic window, press I in order to get components, browse the library, and select NMOS, that is NCSU device FreePDK, and it contains number of PMOS and NMOS. So we can see the extension over here, that is VTG, VTH, and VTL. The VTL are especially for low threshold, VTH are especially for high threshold, and VTG are near threshold. So we will be using the VTL in general, that is NMOS VTL and PMOS VTL. So we'll go for NMOS VTL first, and followed by the PMOS VTL. You can go all the way browsing this particular folder while selecting this PMOS VTL, or else you can do is you can type the name of this particular cell if you know that name, and you can access that particular component. So as we will be considering 2:1 proportion, let's make the width of this particular PMOS twice as that of NMOS. Here we can see the width is 90 nano, so let's make it 180 nano, and length will be 50 nano, and place the PMOS over here. If we zoom in using your scroll bar, you can see the width of PMOS is 180 and NMOS is 90. That is, we have maintained 2:1 proportion. Now we are going to add VDD and ground over here. So in order to make that, again press I, browse, and select analog library. This library contains all the devices, all the components which are related to the analog operations, that is transistors, capacitors, resistors, and everything, voltage and current sources. So we'll be selecting the VDD source, symbol, minimize it, place VDD over here, again go for ground. As I said it before, if you know the name for this particular component, you can type it here. So as I know, GND is the name for ground, you can type it, or else you can go all the way browsing and select that ground from that list. So for now I'm using the shortcut and placing ground over here. Now I'll be inserting pins over here using command P. So my input will be in, make sure that the direction of input is input, hide it, again place it, again press P in order to give your output, make sure that the direction is output, and place your component over here. So we are done with the placement of all the components. So now we are just left with the connections. In order to make that connections, press W and join all the floating points as per your circuit design. So we are done with all the connections, and if you want to save your design or if you want to check for the errors, you can click on this particular tab, which is check and save. Once you click it, it will automatically save this particular schematic for you, and it will also show you the errors. So as you can see here, there are two warnings. In order to spot where exactly the errors are, you can zoom in and you can see the yellow squares over here. Those yellow squares indicate that there is an error. So in order to get rid of this error, we can see that the body connections are missing, so we'll connect those body connections. For PMOS it will for VDD, and for NMOS it will go to the ground. Again, click on check and save. As there is no any pop-up, you can see it is error free, or else you can check your log window and it will show that schematic check completed with no errors and your schematic saved. So after doing your schematic, you're supposed to launch this ADEL. This is one simulator provided by Cadence, that is analog design environment. So click on that. There will be one pop-up for the license and click yes. Again, go to setup and select simulator directory, and you can scroll here like in simulator list, drag down, and you can see 3 simulators over here, and among those 3 simulators we'll be using HSpice HD because it's the only simulator we have available, like it is available with Cadence 45 Nano. So go for HSpice, click apply and OK. Again, we will be going for the model libraries for particular PMOS and NMOS transistors for 45 Nano. So click on model libraries and browse those libraries by clicking over here. You will see one folder by the name HSpice. Double click on that folder. You will see a number of model files over here, that is HSpice FF, HSpice NOM and HSpice SS. FF is for fast, NOM is nominal, and SS is for slow. So preferably we'll be going for HSpice norm and open it. Click apply and OK. Alright, so we are done with the initial setup. Now we are left with the input and output. So in order to do that, go to setup, stimuli, and you can see here the input which are given, that is in, which is DC voltage, but currently it is in off condition. So in order to make it active, you need to click on this enable. You can see the red tick mark over here, and you can also change the function of your input, or you can give any function that you want. So let's make it pulse. So I'll be giving one pulse signal. As we are using Cadence 45 Nano, the maximum supply voltage that we can give is just 1.1 volt. So this is the maximum voltage level that we can maintain in Cadence 45 Nano. Let's say voltage 1 is 1.1 and voltage 2 is 0. Let's make the period is 40 nano. There is no delay time, rise time is 10 pico, fall time is 10 pico, and pulse width is 10 nano, so that we will maintaining 50% duty cycle. And click on apply. You can see that your input is changed from off to on, that is it is active. Again, in order to check for the VDD and ground, click on this global sources. You will see your VDD and ground pin which are provided. In order to make it active or make it on, click on enable. As VDD will be DC, select the function DC and give the voltage of 1.1 volt and click apply. You can see your VDD is in on condition, and then click OK. So you are done with your initial setup, and again you are supposed to choose the analysis. So click on analysis, choose and select the transient analysis, that is the second option over here, tran. Give the start time as 0 nanoseconds, stop time as 100 nanoseconds. You can give any time over here, whichever you want. I mean, it depends on the number of cycles and number of switching. So let's assume that it is 100 nano and with the step of 1 nanosecond. Click on apply and OK. As you can see in this particular analysis window, you have got one analysis for transient, that is one for 1 nanosecond step and 0 to 100 nano. So we are done with our initial setup. Now we will be choosing our output to be plotted. So click on outputs to be plotted and select on design, as we want to plot both input and output. So click on input and output. After clicking that, again go to your analog design environment and click on run netlist and run. It will generate one netlist file and the plot. So this is the netlist file that we have got. It contains the necessary information for your simulation, that is voltages, currents at all nodes, also the capacitances, resistances and everything. You can close it for now. So as you can see, this is a waveform, but this is the combined waveform. We can see both the inputs and outputs over here. You can see the labels over here, that is input and output. So in order to make that separate, let's click on graph and split all strips. You can see the input and output. You can also change the color and width of the particular trace. So to do that, click on right click, go to color, select any color, whichever color you want. Let's make it blue. Again right click, width and medium. We'll do the same for the output. You can also customize your own trace property. I mean, right click on this particular background, go to graph properties. You can also change the background color over here, whichever you want. I will take white for now. OK, apply and OK. So for now we can see the clear waveform for our input and waveform for output. These are the switching points. Now in order to calculate delay, we'll again combine those two traces so that we can compare the switch of input and switch of output together. So again go to graph and combine all analog traces. You can see the waveform which you saw before. So these dark lines are the points which your input and output switches simultaneously, and you can see one scale right above the graph. This scale indicates the smaller version of your graph, and you can zoom in and zoom out of this particular signal. So let's zoom in to this point. So in order to do that, you need to swipe your ruler all the way nearer to that particular point. Again go to other end, bring that particular scale to nearer to your point. By adjusting the points, you can see the switch between your input and output. So this blue one is your input and red one is your output. Again we'll be considering the 50% value, like we'll be calculating the delay by the time, like the time spent when the input reaches to the 50% value and the time when output reaches to 50% value. So by calculating difference between both, we'll calculating the average delay. So in order to add marker, let's click on marker and create marker. There will be three types of markers. First is point, like if you want to add some particular coordinate or particular point, you can give x and y coordinate for that particular marker and you can mark it. Second is horizontal. It means if you know the y coordinate and you can plot it. If you know x coordinate, then go for the vertical marker. So for now we'll going for horizontal marker, as we are considering 50% of input and 50% of output. It will be the value, like for VDD by 2, that is 1.1 volt divided by 2, which is nothing but 0.55 volt. Click on apply. You will see one marker over here. The marker with the blue ink indicates the time when the input reached to its 50% value, and the red one is the time when the output reached to its 50% value. So by calculating the difference between the both, you can calculate the average delay. Yeah, this will be the average delay only because you are not considering all the transitions of this particular inverter circuit. It is easy to calculate average delay for this inverter circuit, but once you move from easier circuit to the complex circuits like NAND gates, flip-flops and clock circuits, it will be difficult for you to go to each and every switch and calculate the delay using Cadence. So we'll be averaging the delay using this type of formula. Now in order to calculate the power, we will be using some previously stored files. So in order to do that, go to your putty window and we will be importing one spice file which is previously stored at server. So in order to access that file, type this command. This command is the same as we have used it for the setup, mapping the setup. It is the same path, only the last part will be different. And the name of the file will be measurement.sp. This is just a one-time copying. I mean, once you have copied this, there is no need to type this command again. So you can access this file later on whenever you want. So after this, click on enter. So you can see the file is copied successfully, and don't forget to give the dot at the end as we have used for previous command. Now in order to access that file, you can type anything like nano or vi. Let's use nano, followed by the name of that file, and click enter. It will open that particular file for you. So for in this particular analysis, we are creating the time from 0 to 100 nanoseconds. So we'll be considering the same time over here in order to calculate the average power and peak power. So let's make it 100. Do the same for the peak power because we need to consider the same time span. And after changing it to 100 nano, you press Ctrl and X. So it will ask you whether you want to save this particular file or not. So type yes, Y, and it will ask you by which name you want to save this file. Then give the default name, that is measurement.sp, and press enter. So you have successfully saved this particular file. Now minimize this putty. Again, go to your analog design environment. The initial setup is done already, so go to setup and add this particular measurement.sp file. So in order to do that, click on this simulation files and add it to this under stimulus files. So browse and select that measurement.sp file which you have previously saved and open it. Click apply and OK. Now again run the setup. There will be the same waveform. Now we don't need the waveform, we need the netlist file, And if you scroll up in your netlist file, you can see at particular point there is the calculation for average power and peak power. Average power is about 40 nanowatt and peak power is 80 microwatt. So using this spy command, you can find the average and peak power which is consumed by the circuit. So in order to save this current state, go to session, save state, and click on cell view and click OK. Once you save this, you can access this ADE setup from the library only. Once you go to library, you can see that particular setup over here is by state. Once you double click it, it will open it automatically for you and you can run it whenever you want. See. Alright, so we are done for the Cadence 45 Nano. In next video, I'll be telling you the layout for 180 Nano and how to make symbols using Cadence commands. Alright, thank you.